Let's go to CheckMate. So in CheckMate, I was assigned this paper, which is very recent. So as you can see, it was published end of February 2020, and it's basically a search for a direct tau production in final states with two hadronic tau leptons. Okay, and so basically we're going to need to incorporate this Atlas paper into the upcoming CheckMate because they're gonna update the version. So of course, one of the things that they're gonna add is the recent CMS and Atlas searches. To be incorporated in the new CheckMate version. Okay, so what's done typically is that you need to be able to also simulate the event that they want. So in here, you need to generate a stau production. Okay, because what's being done is you simulate the signal event that is being predicted by a supersymmetry, and then you compare it with the you generate some background standard model events, and then you're gonna compare it with the data that you're gonna observe at the LHC. And then of course most of the time, because we haven't seen SUSY yet, most of the time your data will look like the standard model instead of looking like the SUSY signal that you generated. So what you typically look for is what are the particular parameters in their generations. For example, here, the simulated signal samples, they use MADGraph to generate it, and then they said that they set the masses of all charginos and neutralinos apart from Chi1 to 2.5 TeV. And then so since all the rest were set into very heavy masses, then the tau can only decay into Chi1, which is another SUSY particle, to the standard model tau. Okay, and so in here they mentioned the masses. So they said they varied it from 100 to 440 GeV. And then the Chi1 is varied from 1 to 200, but you don't need to do that. You only need to look at their benchmark points or the specific combination of masses that they look at. So in here, they look at tau masses of 120 and 280 GeV, and then the Chi, they're looking at 1 GeV. Okay, and then I believe they said the tau left and tau right to be the same and to have the same mass. So we're gonna do that. So we're gonna use MADGraph to generate that particular event that they have. So we open MADGraph, and then we're gonna import. So when you open MADGraph by default, it's using the standard model parameters. Okay, so we're gonna import the MSSM model, which is the model used for, I believe it's called so I believe this is LHA2. We should be fine with this particular supersymmetric model. So MSSM is minimal supersymmetric standard model. So now we have this. So now we're gonna generate a tau pair. So since the left and right are the same, I believe in usual SUSY terminologies, let's look at the Monte Carlo table numbering scheme. The tau left and right, they're usually called 1 and 2. So let's do the one the tau 1. So I believe this will be, so let's produce a tau pair E1 minus. Okay, and then we output this to, let's create a folder called the tau. And then okay, so we're generating the event, and then afterwards we need to edit the parameters of these tau and all the masses. So what did we do? We outputted launch tau. Okay, so we need to shower it with they used Pythia to shower it for their hadronization. So let's do that. So let's turn on Pythia. So that's number 1, and then okay, that should be fine. And then now we edit the parameter card. Okay, the param card, the one option. So as you can see here, these are the default values of the MSSM model when you call it in MADGraph. So what we do is we look for the black for the masses. Okay, so this is the black for the masses, information for the mass. So they set all the charginos and neutralinos. So usually these are the Chis, right? So 1000022 all the way up to 10035. So 10022, let's edit that. They set it to 2.5 TeV. Okay, so that's 2.5 times to the third. So I believe the default masses here are in GeV. So the same for M neutral 2. So 2.500 to the 3. And then the ones that we're gonna use will be Chi1, which is 2.2. Or wait, 2.4. Right? They're using Chi1. So let me set all these other guys to 2.5003, and then this one 2.5 TeV, and then here's our another neutralino. .5, and then 10024. 10024 is a charged. So this is also 2.50000 times 10 to the 3. So I believe we're gonna use the Chi1 neutral 1022. We're gonna set that equal to 1. So this one, okay? We set it equal to 1, okay? And of course the staus. So we have let me see their PDG code number. The first one is 1000015. So I believe it's this one. So they set the mass. What's their first benchmark mass? The first benchmark mass is 120. So we set that 120. So times 10 to the 2. Then 1.2. Okay. And then they said that that's also equal to the right, okay, which is 2000015. So 20015, we set it with the same mass, so it's this one. So 120, okay. And then of course, just to make sure that the staus will decay to the one that we produce, which is the 1000015, will decay to Chi1 and the standard model tau. We go to the decay block. Okay, so the decay block is somewhere. Where is it? Somewhere over here. Okay, so 1000015. This is the one that we produce. So we add here 2, which means, I don't know, sorry, 1, that's the branching ratio. 2, which it means the number of final outputs, and then so we want this particular tau to decay to a the Chi0, the neutralino, so this number, and the standard model tau, which is of course the standard model tau has PDG code number 15. Okay, so okay, there you go. So now that we've edited our write and quit, now that we've edited the parameter card, let's edit the run card, because we want to produce so now in order to do the validation, aside from the paper, this contains all the physics and the discussions, it also has a corresponding, so each Atlas publication or CMS publication, they have a corresponding HEP data. Okay, so if you look at the HEP data, you'll see here like all the relevant numbers. Not everything are found on the paper, because if they put this all on the paper, it won't look nice. Okay, so for example, one of the things that you don't typically find on an Atlas paper is the cut flow for the different selection cuts that they have. So for this particular benchmark point with the tau 120 and chi 01 mass of 1 GeV, this is the number of events that they're looking at. Okay, so 26,792. So let's say we generate let's say 27,000 events. Okay, so that's the number of events that we're gonna generate, and then of course this is 13 TeV. So okay, so 6565. So that's fine. So we have right width. Okay, and then after that, after you edited the parameters for the values of the masses and the particular decay that you want, and then the number of events that you want, we should be able to run it now when you press enter. Okay, and so now you wait. Okay, and so now that you've done that, so you wait. So it typically takes long because it's like 27,000 events. But now after you've done that, then we're gonna go to the particular the very relevant part of the validation, which is this the analysis code that you need to incorporate into CheckMate. So now you're gonna look at the specific cuts that they require for their the observables that they're looking at, and then you usually see it in the event reconstruction. For example, the jets are required to have a PT greater than 20 and eta, absolute value of eta, pseudo rapidity of 2.8. So you see that here. Okay, the requirement for the jet. You have like a requirement for the electron, for example, with the PT greater than 17, and so on. Okay, and most importantly, you need to apply the cuts one by one. So this I'm still doing. So for example, for the SR low mass is the tau is equal to 120. High mass is when tau is equal to 280. Yeah, okay, so 280. So we're still looking at the low mass signal region. Okay, so for example, one of the cuts that they require is ET miss. The ET miss has to be less than 150 but greater than 75. So now I introduce that here. So if my missing ET does not satisfy those particular cuts, then I reject the event. So you just ignore that event. Okay, so you incorporate all these particular cuts. So you have a requirement for the light lepton, you have a requirement for delta R, and so on. Okay, so you incorporate each of these in the analysis, and once you've done that, you run the particular analysis on the Monte Carlo events that you generated. Okay, and then after you've done that, then you have this thing called a cut flow comparison. So it will look something like this. Okay, so this is an existing CheckMate validation for another Atlas paper, this one in archive. Okay, but basically what the result that should look something like this. So for Atlas, you have the cut flow. So this is the initial number of events is 19,900. When you have this missing energy requirement of it being greater than 200 GeV, then the number of events left should be 476. So now your CheckMate validation, your CheckMate analysis code should be able to do that within the confines of the uncertainties of your MAD graph, for example. So you get something like this. So I need to do this. So I need to do this cut flow, and then for that event that I generated for stau, and then I need to compare it with this particular column right here. So for example, so I generated 27,000 events, for example. We can change that to something near, like, I don't know, 26,800. But anyway, after you introduce, for example, the BJet veto, according to Atlas, they have 892 events left. So is the number of events left according to CheckMate, is it nearer that value? So that's how you do the validation. Okay, so if it should be 892 and then you get something like, I don't know, 10,000, then there's something wrong with your validation. So that's why you do the validation, to make sure that the cuts being imposed by CheckMate is very near the ones that were imposed by Atlas. So that way we can, that because CheckMate, what it does is it constrains your model depending on existing Atlas and CMS analysis. Okay, depending on existing data, and then it basically says that a particular benchmark point that you're looking at is excluded or accepted based on current Atlas and CMS events. So basically that's what I'm working on. But yeah, right now, this is the hard part. Okay, the analysis code for validating this particular paper. And then after I'm done with this, after I've incorporated these cuts, and if they work, if they're nearer the actual atlas cut flow, then Jong's gonna give me another paper. Okay, I think another 2020 paper for mm, to be analyzed. Okay, but anyway, also our multi-Higgs paper. Okay, it's almost done now. It's with Christian, my collaborator from Italy, and it's in a point where we already have like the final draft, and then he said if we're okay, then he will send it back to PRD with the reply to the with our reply to the comments of the referee. So we now have the replies of the almost 20 calls of it, 17 comments of the PRD referee. We're gonna send it back, and then hopefully I don't know, it gets accepted, or hopefully the new additional changes would be minor. But anyway, this has been postdoc week number 89. Okay, and here you're looking at the workflow of the current tasks that I'm doing. And I'll see you next time. Thanks for watching. See you on Postdoc Chronicles week number 90. 90 weeks of postdoc. Okay? Thanks for watching, and bye-bye.